morning, everyone. It's my pleasure to be here, to be involved with this meeting, and to share my presentation with Professor Thierry Passeron. So we'll be talking about the impact of sun rays on pigmentation. So pigmentation is regulated by more than 170 genes, so it is a very tightly regulated function in the skin. And the diversity of the variant of the gene determines the diversity of the pigmentation phenotypes, and also the diversity of pigmentary response to sun rays. Because melanin absorbs UV rays, we know that pigmentation is inducible by sun exposure. Then here in this talk, we will be reviewing the impact of the different UV wavelengths, the UV domains on skin pigmentation and even beyond UV rays. So let's start by UVB. So the impact of UVB has been studied for years because the UVB domain is the domain which is responsible for sunburns, DNA lesions into the skin. So these rays does not penetrate very deep, but they are very energetic. So they generate DNA lesions, and then the release of P53 that you probably know as being the guardian of our genome. And within keratinocytes, among all the defense mechanisms which are involved, regulated by P53, there is a release of alpha MSH, so an hormone that released by keratinocyte and that control and activate the synthesis of melanin within melanocytes. UVB has also a direct action on melanocytes through these different pathways that I won't detail today. So, in conclusion, UVB induces new melanin production via as a defense mechanism after DNA lesion generation and P53 release. A good protection toward UVB seems unquestionable for skin health and to prevent sunburns and DNA lesions. And then SPF 50 cream, a high SPF sunscreen, is mandatory, and also, as you understood, will prevent the production of new pigment. Then, when it deals with the regulation of pigmentation with UV rays, we also have to consider the UVA spectrum. So this is kindly demonstrated in this study on the top of the slide, where the back of the skin of some healthy volunteers was exposed to a single but acute dose of UV. Then on the left, there were the same sunscreen sun protection factor of 50. But on the left, the UVA protection factor was less than on the right, where the UVA protection factor was much higher. And you can clearly see that the photoprotection in both sides is not the same. The efficacy of the sunscreen with the highest UVA protection factor is much higher than the lowest protection factor. And the same conclusion can be done with the second study on the bottom of the slide, where once again the same SPF was used, but different UVA protection factor, and with the strongest protection factor in the UVA domain, the pigmentation was preserved versus the lowest one. Now I would like to make a focus on long UVA. So long UVA are at the end of the UVA domain. Long UVA have low energy, but they penetrate very deep into the skin, and they represent roughly 80% of the UV rays that reaches the skin. So we thought it was super important to understand the impact of long UVA on the skin. So we led some experiments thanks to our reconstructed skin in L'Oreal, and we've shown that long UVA also generate the generation of reactive oxygen species. So after exposure to long UVA, you can see a high increase of reactive oxygen spacing, meaning increase of oxidative stress. But also long UVA generate DNA lesions as well. At the skin level, we've demonstrated at gene expression level that whatever it was in epidermis or in the dermis, we also have numerous functional families that are altered, including inflammation, cell integrity alteration, and also immune response following long UVA exposures. Last, in vivo, the impact of long UVA was studied in this nice study published in 2017, where some volunteers with different phototypes, with highly pigmented skin until lowly pigmented skin, were exposed to the same UV dose of long UVA alone. And then we've shown that whatever the skin type, long UVA induce dark skin darkening with the same intensity. So a high skin darkening and same intensity, whatever the skin tone. And behind this pigmentation, we also observe at gene level that behind the pigmentation, there are also skin alterations, so inflammation and oxidative stress. So now it is clear that when it deals with prevention of skin darkening and pigmentation disorders toward sunlight, it's important to be protected from UVB, UVA, short UVA, but also long UVA. Now, I'm glad to introduce for the first time to this audience this new long UVA filter that was approved recently, so in 2020, by the European Authority for Cosmetic Products. So MCE, as an abbreviation of the inky name that I won't pronounce, is now commercialized under the trade name of Mexoryl 400. MCE is very efficient, so new UV filter, very efficient in the long UVA wavelength. So you can see that the peak of absorption is within the long UVA. Sorry. Then on the right, we compared the absorption capacity of a sunscreen containing a UVB and UVA filtration, so a classical sunscreen, and the absorption profile when it was associated to MCE. And what you can see in the dark black curve here is that the reference formula have a very good protection within the UVB, within the UVA, but when it comes to long UVA, the protection and the absorption capacity is much lower. And then by adding MCE to this sunscreen, you can see that we are indeed enlarging the UV absorption profile in the entire UV domain. So the impact of having MCE within a sunscreen has been studied first in vitro. So once again, we use the reference formula in red in the curve with UVB and UVA absorption, and we added and we used two other formulas with MCE in different concentrations, so in green and purple. So you can see that the absorption spectrum is indeed higher in the long UVA. And then when we look at the impact of this, the addition of MCE within the sunscreen, we can see, for instance, here on the dermis compartment, that long UVA with no protection, so the no formula, leads to a drastic decrease in the number of viable fibroblasts, so a loss of the fibroblasts, a disappearance of the fibroblasts with no protection. So when we use a classical reference formula, we are indeed protected from this disappearance, and in presence of MCE, we have a much higher and significant protection. This was also evidences on other biological functions, where here you can see on this gene expression for oxidative tests, for instance, in white, you have the impact of long UVA. In red, you have the impact of the reference formula, and in purple, the impact of a sunscreen containing MCE. Then you can see that long UVA induces drastically oxidative stress, for instance, which is prevented by a reference formula. And then MCE have a significantly higher efficacy, and this was the case for inflammation markers, the quality of cellular matrix, and as well oncogenesis and viral defenses. Last, in vivo, we assess also the impact of adding MCE to a sunscreen. Here we have two sunscreens with the same SPF and one containing MCE in blue. And this double-blinded randomized study was led on the back of volunteers that were exposed to long UVA. And then without protection, the decrease in delta L or delta ITA give rise to reflected skin darkening. And without protection, you indeed have a significant skin darkening, which is prevented by the reference formula and improve when we have MCE within the sunscreen. So this to say that finally, when it deals with managing skin pigmentation by managing the UV and sun rays, it is important to consider both UVB, UVA, and long UVA. Now, what about the wavelengths out beyond UV light, in particular visible light? So it's known from years that visible light also modulates skin pigmentation. So this was nicely demonstrated in 2020 with the first study on the top, where some healthy volunteers from different phototypes, starting from 2 until 6, were exposed to visible light. And what was shown that visible light indeed induced pigmentation only in the phototypes, phototype above 4, so 4, 5, and 6. And the first skin, we did not observe any pigmentation in first skin. So this pigmentation induced by visible light is very specific to the skin tone. Also, this visible light pigmentation was compared to long UVA-induced pigmentation, and what has been shown is that visible light induced a much more prolongated and intense pigmentation when compared to long UVA. So very important parameter also to consider, particularly for the darker skin tone. Then in the second study on the bottom, it was not, this study was led with natural sun exposures, meaning that it was not a simulated exposure with a solar simulator, but only the ambient light that was modulated thanks to physical filters. So the physical filters were put on the skin, and the volunteers were exposed to the ambient light. Then this was done to demonstrate that even the visible light within the ambient light modulate pigmentation. And as you can see here, visible light modulates pigmentation, UV as well, and the addition of both give highest pigmentation, meaning that there is an additive effect between these wavelengths. So now I will let Professor Passeron, to finish this talk.
Thank you. Thank you very much, Peggy. Good morning, everyone. It's my pleasure to be here, and I would like to thank Skinalliance for inviting me to this 2022 meeting. As Peggy nicely showed you, I think it's really important to keep in mind that usually when we talk to our patients, they mostly look at the UVB, and they are looking, when they're looking for sunscreen, they are just looking at the SPF. But when it comes for skin aging, but also for pigmentation, but it's not here the topic, but also for skin cancer, the long wave UVA are very important, and as most important as UVB. And when it comes to pigmentation, we have to think about the visible light. And and as Peggy just showed you, long visible light is able to induce and very potent and long-lasting hyperpigmentation, especially in darker skin types. So after that, it's very important to understand what kind of wavelength, what kind of visible light are able to trigger this hyperpigmentation. So a couple of years ago, we compare the blue and the red light on the back of healthy volunteer, and as you can see on this slide, when we exposed to the blue light, we have a very nice dose-ranging hyperpigmentation with the blue light. When we expose to the red light, there is absolutely no impact on pigmentation. And you can see how prolonged is the hyperpigmentation. After 3 weeks, there's still some hyperpigmentation and even sometimes longer. So the second question that raised is, what are the mechanisms involved in this visible light-induced pigmentation? So just to summarize this first part is that we were able to demonstrate that it was the high energy visible light, meaning the blue and the violet light, that are responsible for inducing hyperpigmentation. Very importantly, we used physiological doses. And in fact, it's about 1.5 hours, 2 hours of sun exposure. And it's very important because in daily practice, you're going to have a lunch outside. You use a very good UVA and UVB sunscreen. But during your lunch, you receive enough blue light to worsen, for example, your melasma. And that's very important for clinical practice. So as I was mentioning, after that, we have to know what are the mechanisms involved, and does this visible light has any effect in pigmentary disorder. So I won't go into details, but we were able to demonstrate that, in fact, in our skin, the melanocytes have the ability to really see the blue light because they have, as we have in our eyes, the same type of receptor. They have opsin-3, and opsin-3 sense the blue light, activate the pathway that ultimately led to the increase of melanocytic enzyme such as tyrosinase or TRP1 or DCT. And very interestingly, when opsin-3 is also able to put in complex tyrosinase. And when tyrosinase is complexed, it stabilizes its activity, explaining why we have such a prolonged hyperpigmentation after being exposed to blue light. So as soon as we demonstrated that it was the blue light, we have a lot of questions from colleagues, journalists, and patients for what about the blue light we are receiving every day from the screen of our devices. So indeed, it's the same type of wavelength, but what we have to keep in mind is the intensity, the irradiance. And of course, this is not the same. We calculated that the intensity that we're receiving for the most powerful screen of devices is 100 to 1,000 less intense as compared to the blue light we are receiving from the sun. Meaning that, and you can understand easily that if we are receiving, for example, 60 joules in 2 hours or in 2 weeks, you won't have the same effect on your skin. And 2 years ago, we demonstrated, in fact, that indeed there is not the same effect. We exposed a melasma patient, and we're going to see that melasma is very sensitive to blue light. We exposed only half of the face to, we calculated the maximum dose that we can receive by being in front of the most powerful TV screen at 20 centimeters, 8 hours a day. It's very difficult to do that, but some children can do that. And in fact, we calculate that we expose for 1 week, and we calculate the pigmentation. And you can see on the graph that there is absolutely no differences, meaning that you won't get tan in front of your screen of your devices, but you already saw that. And also, you can reassure your patient because they won't get worse than melasma, actinic lentigo, because the intensity is too low. So yes, for the sun, not for the screen of the devices. So the next question is there any usefulness for our patient with melasma? And in fact, several years ago, we made a study in melasma patient. We included all the patients at the end of our winter, so in April, and half of the patient received a very good UVA and UVB protection, and the other half received exactly the same UVA and UVA protection, but on top of that, they received also protection against blue light. And as you can see here, there was significant differences at the end of the summer. So we saw all the patients in September, and there was significant lower relapses of melasma when you had protection against blue light. So And very interestingly, some Mexican colleagues demonstrated exactly the same with the same type of study, UVB and UVA against UVB, UVA, and visible light. And as you can see here, it was much better when you protect also against visible light. And more recently, some Indian colleagues made the same type of study in actinic lentigo. Again, UVB, UVB, UVA, UVB against visible light, plus or minus visible light. And you can see that only when you completely protect against UVB, UVA, and visible light, you can decrease the pigmentation of actinic lentigo. But if you only use UVE and UVB, you don't decrease the pigmentation. And last but not least, what is very important for our patient in our practice is post-inflammatory hyperpigmentation. And probably you saw that patients using very good sunscreen, despite the use, they have some PIH. And we developed a model. And in this model, we were able to demonstrate that only ambient light is enough to trigger PIH. And the best way to prevent it is to use opaque dressing. And it's opaque dressing for 2 to 3 weeks. And it's well demonstrated. And there was a nice Korean paper demonstrating this also. So, but we cannot only always protect it with opaque dressing. So if you can't, you have to use, again, a sunscreen protecting from the UVB to high-energy visible light. So nowadays, there was a lot of data on visible light and pigmentation. In physiological conditions, skin type 3 and higher can get tan with visible light. But any type of skin type, when they have pigmentary disorder, including melasma, actinic lentigo, and PIH, are prone to develop pigmentation when they are exposed to visible light. And it's nicely demonstrated that if you combine long-wave UVA and high-energy visible light, and it's very interesting to see that those wavelengths are more closer. UVA are more close to high-energy visible light than they are to UVB. And to combine together, they are increasing even more the pigmentation. So the clear and practical conclusion is that for when it comes to pigmentation, the optimal sunscreen should protect not only against UVB, but also against long-wave UVA and high-energy visible light. So very rapidly, can we protect against visible light? The answer is yes, but we have to use physical shields, tinted products containing, for example, iron oxide. And you can see here in this slide that when we use increasing amount of iron oxide, you can nicely prevent this hyperpigmentation. So recently, we made some, with a group of experts, the recommendation to assess the visible light protection, because you can see that many brands are saying that, okay, we protect against visible light, just, for example, by using antioxidant. Unfortunately, this is not enough. You have to use iron oxide so far to prevent the photon to stimulate the opsin-free. And the best method is the in vivo method to demonstrate if a sunscreen is really able to prevent from visible light-induced hyperpigmentation. And very recently, we were able to demonstrate that, in fact, we can also use the transmission of the visible light. And what was very interesting is that there is a very nice correlation between the transmission and the hyperpigmentation in vivo. And when we measure just by calculation what was the critical wavelength, is the wavelength from 400 to 465, which is exactly the wavelength of the sensor opsin-free. So it's very interesting and can be very useful to develop a new sunscreen to protect against visible light-induced hyperpigmentation. So to conclude, I would like to stress this recent publication that we made with help of La Roche-Posay, but with a group of international experts, because we have a lot of knowledge now on what type of wavelengths are important, depending on the skin type, the skin latitude, and the dermatosis. And we have to use a tailored photoprotection. For example, we know that for UVB is mostly important for fair skin type. Peggy showed you that UVA, we are all equal. We are all sensitive to long-wave UVA, but when it comes to visible light, it's mostly the dark-skinned individuals that are more prone to respond in physiological condition. So to conclude, it's now very well demonstrated that wavelengths of solar radiation beyond UVB and UVA have clearly an impact on visible light, that long-wave UVA, but also high-energy visible light are critical, especially when it comes to pigmentation, but it's the blue light coming from the sun and not from the skin of devices. And very interestingly, we sense the blue light as we sense the visible light in our eyes. And finally, and I think it's obvious now, when it comes for a darker skin type, but also for people with a pigmentary disorder, we really have to advise sunscreen covering UVB, long-wave UVA, and visible light. And I would like to thank you for your attention.